Hello, everyone. A new physical chemistry chapter, third law of thermodynamics, is going to be started here. In its first lecture, the Nernst heat theorem and its application will be discussed. But before that, we have to restate some preliminary relationships of thermodynamics. So, some necessary expressions involving delta G, delta S, and delta Cp will be restated here because this will be applied accordingly. So we know the mathematical definition of Gibbs free energy, which is G equals to H minus Ts. G is Gibbs free energy, H is enthalpy, T is temperature of the system, and S is entropy. Now, from the combined form of the first law and second law, we have derived four fundamental equations of thermodynamics, one of which is dg equals to vdp minus sdt. So by just rearranging this equation at constant pressure, we can get this equation del g del tp equals to minus s. So if we put the value of minus s in this expression, then this expression of g would become g equals to h plus t into del g del tp. And for finite changes, we can also write this instead of g, we can write delta g. Instead of h, we can write delta h. And instead of this g, we can write delta g. So for finite changes, we are writing here delta g equals to delta h plus t into del of delta g by delta t by del t at constant pressure, which is in turn the Gibbs Helmholtz equation. So this is one of the relationships, and we have to rearrange these equations. We have to take this term in the left hand side and the rest of the terms in the right hand side, and thus we get this first expression. This is expression number one, which will be utilized later on, where it is stated that T into del of delta G by del T at constant pressure must be equal to delta G minus delta H. Next, since we know this fundamental thermodynamic equation, dg equals to vdp minus sdt. So from here, we have already written that del g del tp must be equal to delta s at constant pressure. Okay. Now, if this entropy expression, we have to derive this at in case of finite changes. In place of s, we have to write delta s. And if we write delta s here, then here we have to make the change by writing delta g instead of g. So in that case, we can get yet another relationship, which is del of delta g by del t at constant pressure must be equal to minus delta s. This is the second relationship, okay, which will also be utilized later on. Now we know the expression of heat capacity at constant pressure, which is del H del Tp. We know that. And this H enthalpy becomes enthalpy change at finite for finite process. Then this Cp becomes delta Cp. And this is the relationship where H is changing finitely, as well as conversely Cp also changing by following a finite process. And this equation is well known, very much well known to you, which is actually the Kirchoff's law. Okay, so this is the third relationship which will also be utilized accordingly. So we have three relationships. The first relationship is this one, the second one is this one, and the third one is this one. So just have a look. These three relationships, keep them in your mind. They will be utilized. Now the Nernst theorem, the main topic of this lecture. So this theorem states that the entropy change delta S for a reversible process in a condensed system goes to zero as the temperature approaches absolute zero. That means the system is solid, particularly. That means the condensed system. And there some changes are taking place, but these changes are following the reversible path. In that case, the overall change in entropy, okay, that is delta S, which becomes tinier. That means which becomes smaller and smaller and approaches zero if the temperature drops towards absolute zero. So this is the Nernst heat theorem. And in order to derive this equation, we have to go through two states. One is initial state, which is state 1 simply. Another is final state, which is state 2. And if so, state 1 and state 2, in that case, we can write delta H as G2 minus G1, that is G final minus G initial. Similarly, the expressions of delta S, delta H, and delta Cp. S2 minus S1 is delta S, H2 minus H1 is delta H, and Cp2 minus Cp1 is delta Cp. Okay. Now, the first relationship, which is the Gibbs Helmholtz relation, we have already derived this relationship. So, no need to further explain anything about this relationship. In this relationship, you can see that there is a differential relationship, and which is multiplied with temperature. So, simply, if you decrease the value of temperature T, then the right hand side will also become tend to be equal to 0. This one at t tends to 0 becomes tends to 0. So this one also conversely will tend to become 0. And this is the Nernst heat theorem. Okay. Now the mathematical consequences. So we can here write at t tends to 0, this term is equal to 0. Therefore, this one also becomes equal to 0. And if this one is equal to 0, then delta G must be equal to delta H. And from the EMF measurement of cells, it has been found that with decrease in temperature, this term goes on decreasing asymptotically. And at absolute zero of temperature, the values of this one and this one, they become 0. That means the limiting value of del delta G by del T at constant pressure at T tends to 0 is 0, as well as the limiting value of del delta H by del T at constant pressure at T tends to 0 is also equal to 0. And this is graphically can be this one graphically can be represented by this one. Look at this low temperature at near about absolute zero. These two curves, one representing delta G, another representing delta H, they meet asymptotically. That means they seems to be meeting, but actually not meeting. Okay, there must be some gap. So this is the nature of asymptotic graphs. And here at higher temperature, suppose near about the room temperature here or here, as we know that delta G equals to delta H minus T delta S, so this gap is nothing but minus T delta S. Okay. So this is the graphical presentation of the conclusion of the Nernst heat theorem. Now, since we have already derived what we have derived, this is the third relationship we have already derived. No need to mention anything about that. And this one, the second relationship, this one also has been derived in the first slide. So, since this one becomes 0 at t tends to 0, and this one also becomes 0 at t tends to 0, then conversely, delta Cp and minus delta S will also become 0 at t tends to 0. So, we can conclude that the limiting value of delta Cp at t tends to 0 must be equal to 0. And the limiting value of delta S at t tends to 0, this one will also be equal to 0. Minus delta S if 0, then plus delta S will also become 0. And this is the first equation. Okay. That means at the vicinity of absolute 0, delta S, if delta S becomes 0, then S2 equals to S1. That means the final entropy is almost equal to the initial entropy. Similarly, the final heat capacity is almost equal to the initial heat capacity. And that's all. So this is actually the prelude of the third law of thermodynamics, which will be discussed in the second lecture of this topic. So that's all about the Nernst theorem. Now we move on to its applications in thermodynamics, as we have said, to calculate the absolute entropy of substances. So absolute entropy can be calculated with the use of this Nernst theorem. In cryogenics, that means low temperature science, it is used to study the superconductors. In chemical kinetics, this theorem is used to predict the feasibility of a chemical reaction at very low temperatures. In the statistical mechanics, it is used to link the microscopic and macroscopic thermodynamic properties. Here, one thing, the residual entropy will come. in statistical mechanics that you will also learn in the next lectures. So that time it will be discussed. Number 5, in material science, it is used to study the phase transition under extreme conditions. And number 6, in quantum mechanics also, it is used to understand the quantum states of the superconductors. So the conclusion of the Nernst theorem, we have at temperature T tends to 0, this one equal to this one, final heat capacity equals to initial heat capacity at low temperature, and final entropy equals to initial entropy. So from here, the Planck states in his law that the limiting value of entropy at T tends to 0 will also be equal to 0. Since here we are saying that delta S 0 and Planck is saying that S is becoming 0 at T tends to 0. Okay, this is the conclusion. And this fact leads to the conclusion that in the neighborhood of absolute 0, the heat capacities as well as the entropies of all the substances in the condensed state are identical. As a result, it can also be suggested that at absolute 0, all the substances have the same heat capacity as well as same entropy. And the prelude of the third law of thermodynamics, according to the consequences of the Nernst heat theorem, delta S becomes 0, that means S2 becomes S2, S1. It can be said that the entropy change of a process involving solids becomes 0 at absolute 0 of temperature. So that's all about this first lecture. Thank you and have a nice day.